Ladies and gentlemen, hello and welcome back once again to the Operational Intelligence Market Overview here at Inside Analysis. My name is Eric Cavanaugh, CEO of the Bloor Group. We're running this market overview to really give our audience a better understanding of what kinds of technologies are involved in the operational intelligence space. Of course, some of them are targeted applications, and sometimes we're going to be talking to vendors that are in a supporting role for operational intelligence, and that would be the case today. We're going to learn about Aerospike, which is a database. We're going to learn about how they facilitate operational intelligence. And we'll be talking to Srinivasan. He is a founder and VP of Engineering over at Aerospike. So with that, Srini, let me hand the floor over to you and let us know what you guys do and how it fits in the whole space of operational intelligence. Go ahead.
Thank you for the introduction. Aerospike has been focused on solving all kinds of problems in the real-time big data area of Internet applications. There is a lot of applications like real-time advertising, and we have shown a few of them in our additional ones here, like industrial process monitoring, health monitoring, traffic monitoring, etc., where a number of real-time actions happen, and then a software program, in our case, the Aerospike application, is responsible for processing these real-time events and then intelligently interpret it and make sure that the right actions, which are correct for the businesses, happen. Now, the characteristics of these, in terms of an example, if I give you the most important example that we have, where we have deployed widely, is in real-time advertising, where a display ad is positioned in various places of a web page as a user accesses a web page on a PC or a mobile device like an iPad or an iPhone. What happens then is a small real-time bidding auction happens behind the scenes for placement for a specific user. And a lot of information about the current user, about the actual interaction, what they have done recently need to be taken into account, like whether they have seen the ad just before, for example, how much to bid for a user, etc. All of this has real-time SLAs attached to it, and therein comes the interesting problem. So the operational intelligence here needed is to decide within about 100 milliseconds or even 50 milliseconds what ad to show, and then show the ad within about 150 milliseconds. If you don't do that, the user is gone. So that is the level of SLA we have to provide there. And then there are other systems that Aerospike works with in the background, like the data warehouse we have shown in this picture, where maybe every day or a few hours, a bunch of analysis happens, and that information in terms of modeling is fed into the real-time server, which is Aerospike. So let me move on to, yes. Please.
Okay, good, go ahead.
So in order to solve these blistering SLAs, Aerospike has invested a lot of time and energy in developing really important technology. There have been several important goals here, but the most important are to make sure that we can obey the SLAs and keep the service up 100% of the time. The other thing we focus on is to make sure the data is consistent. We are a database. We want to provide the durability guarantee of never ever losing data. Since the data is necessary for running your operations in real time, it is really important that the right data is available at the right time. In addition, most of these applications require a lot of increased capacity. Essentially, we want to keep the costs down by making sure that we utilize the resources available in every individual machine really well. This is the vertical scaling work that we do in terms of making sure that we can use multi-core, multi-processors really efficiently. We also work a lot on horizontal scaling to make sure each of these really fine-tuned individual nodes, as we call them, can work together as a cluster with linear scalability. In terms of actual SLAs, we attempt and we have delivered 99.9% of these transactions to be less than 2 to 3 milliseconds, and we can run up to 1 million transactions per second. In production, I think they have some of our customers have already reached 500,000 transactions per second. One of the important things about Aerospike is we are a read-write database. If this were only a read database, the problem is immeasurably easier. However, we chose to tackle the harder one, which is actually more important in an operational intelligence point of view. Because of the way we can use SSDs or native flash, we basically developed a bunch of algorithms to efficiently use them, and we can deliver enormously high write rates while also sub-millisecond reads using SSDs. Since SSDs are much more efficient in terms of their power utilization, I mean, what happens is if you use SSDs, you can put more storage than you can put in main memory within the same node. You end up reducing the number of nodes, thus reducing the cost of management, the cost of power especially, and also for ease of maintenance. So this gives you, based on a publicly available kind of independent report, using SSDs gives you about 17 times more efficiency than just using a main memory system. Because of the way we have this extreme vertical scaling and horizontal scaling, and we also provide replication, all of this gives you the ability to have essentially zero downtime of the service. And that's what we have delivered over the last 3 years. A little bit about our customers. First customers was AppNexus. They launched 3 years ago, and they have since doubled, I think, pretty regularly every 6 months. I believe their publicly available information is they have about 39 to 40 billion auctions per day. That comes to about 500,000 transactions per second or greater. And we run large installations, and there is BlueKai, who's been a customer for over 2 years, Excelate also, who actually has a very interesting business where they keep all their real-time data available at 4 or 5 data centers worldwide, available all the time. It gives them extreme availability and enables, in fact, actually enable them to survive one of the data centers in New York going down because of the superstorm Sandy last fall. And because of our customers, we actually handle probably, we don't know the exact estimate, but about half of the, our installations see about half of the transactions on the internet for real-time advertising. We are basically behind Facebook through some of our customers, behind Microsoft Exchange, the advertising exchange, also eBay, Orange, and so forth. So our customers actually support all these other customers' basic internet transactions. A little bit more detail on DRAM versus native flash. I already spoke about it. Essentially, we built our own raw file system on SSDs. What this enables us to do is to harness the new kind of behavior of SSDs. Now, if you look at the way SSDs work, they actually have reduced the distance of the data from the CPU in terms of time, right? I mean, if you look at the evolution of databases, 30 years ago, the database technologies developed had basically one overwhelming purpose, apart from the application development case. They just wanted to make sure that they can keep whatever data they can in main memory and make sure that systems actually worked efficiently. So all of it is essentially to figure out how to manage slow main memory with fast main memory with slow rotational disk. The presence of SSDs gives us the ability to give, with the right algorithms, to provide maybe 100x performance boost over traditional databases, and that's what we have harnessed. So we return our own file system, which is based on a log structured file system idea. We do a copy on write, and we are able to continuously write at very high rates, while also reading at very high rates on the same database with absolutely no inconsistencies. And that is basically our contribution here.
Yeah, can you talk very quickly on, if you could go back to that last slide? Just go back one. There you go.
Yes.
On the left-hand side, you've got all indexes in RAM for low wear. Can you talk about that? Because I've heard and read some things about wear and tear using that kind of storage. Can you talk about what?
Excellent. Yeah, the wear and tear on the storage for SSDs, that's a good question, is essentially because if you write to the same location on an SSD over and over again, it only can take so many writes, after which that particular cell dies. And this is called wear, so what we have to do is what is called wear leveling, and we want to provide predictable performance. So there is a kind of a balance here. So the way we provide that is by reserving some amount of memory for storing index entries. So which means any index lookups does not use any flash storage, for example, any SSDs. So when you do reads on an SSD, you make sure that we only read the data from the SSD, and that is only reads. That doesn't involve where leveling. And then the writes, the copy on write is the one which solves the where leveling problem in SSD, because we always write to a new location, and we also use what are called large block writes. So the actual number of writes we do in SSD is a lot less than if we would do in-place updates on the SSD itself, and that would not work very well.
Right.
Does that answer your question?
Yeah, it sure does. Thank you.
So I already talked about the 17x better TCO, and this is done by the Wikibon people. I also just want to point out the native flash performance of Aerospike is superior by far as you look at these throughput numbers to comparable databases like Cassandra, MongoDB, and Couchbase. But Couchbase in this benchmark done by a third party, Thumbtack, could not even load the data. And essentially, the reason, as I said, it is not I mentioned 100x performance boost over traditional technologies. That's what you see here, because not only are we creating a boost. If you build a brand new database using rotational disk, which is what basically Cassandra and Mongo have done with a lot of memory usage, but if you don't actually customize it for SSDs, you still don't get the performance boost at the level of what Aerospike has done. So we are actually focused on it, and that's why we are so much better. If you look at our latency on the right side of the graphs, what you see is our latency is very predictable, and this again is because of the in-memory index that we have and the what I would call limited reads that we do from SSDs itself. So we're able to very carefully control the way we use these various pieces of the system to maintain that level of stability in terms of latencies. And this is extremely important, especially as we go to the next slide, when you are in the presence of failures. So what we have here is a screen capture of a particular installation of a 4-node Aerospike cluster on really cheap machine. This is about a three-year-old system. For $500 a piece, we bought Intel i5-based systems with 16 gigabytes of RAM, and what we did was we can run about flat out 250,000 transactions per second. So what you have is 5 phases. We're running the system. First is really bringing it up and running it maybe at 100,000 transactions per second across the system, and then we run it flat out. So we end up getting 1 million transactions per second total if you look at the graph on the top left. And each of the individual boxes have about 250,000 transactions per second. Now, in real production, one doesn't run things flat out. You typically run at about 40% of capacity. So we drop the throughput to keep it to around 400,000 transactions per second across all nodes. Okay, which means about 100K TPS per node. That's what you see in the graphs in phase 3. Now, we then drop the third node, which means the system has a total capacity in 3 nodes of about 750,000 transactions per second. So if you drop a node out of a 4-node cluster, you still have enough headroom. So you should be able to run at 400K TPS, and that's exactly what this shows. The interesting thing here is we don't have that much of a downtime, if you will. There's virtually there's a minor glitch, and then the system is back at 400K TPS on 3 nodes. And you can see below, each of the existing nodes which are alive or running have immediately taken up the extra load to be 133K TPS. Now, the amount of data in the system, we actually have 2 copies of data here, which means losing 1 node means that all the data is still there. So you can still go at that rate. And then we bring the node back up, then what you can see there is the system again goes down to 100K TPS per node and back to 400K TPS, and you can see the flat line on top between phases 3, 4, and 5. And on the right, you can see that the latency, the top right, the latency is always stayed well under 1 millisecond. In average across all of these transactions. And this is essentially what you get when you mix the extreme vertical scaling that we do, the high performance that we have on a single node, and we mix it with the self-management components of it and scale it out across nodes. And then what we end up doing is replication, and then that gives you 100% uptime. Finally, I guess I'd like to spend a little bit of time on the architecture as to how we actually achieve these particular goals we talked about. Our system is a shared nothing system where every cluster node is identical and it handles both transactions and long-running tasks. We have intra-cluster replication supported with immediate consistency. So within a cluster, in this picture I've shown 3 clusters. The first one is blown up, and there are 2 other clusters in different data centers. Think of one of them to be in California, other one maybe in Texas, and the third one in New York. So the distance between these clusters is quite large, which means that there is about 80 to 100 millisecond delay between messages between data center 1 and data center 2 and 3 respectively. What you end up having is you can build an immediate consistency system with ACID in an intra-cluster sense where we can maintain the SLAs of sub-millisecond latency at high throughput. However, when we go across data center, we do not do synchronous replication. If we did that, then we wouldn't be able to maintain a sub-millisecond latency. And we felt that across data centers, it is more logical to have an asynchronous replication strategy. And this has actually worked out really well in practice. So
yeah, that's very interesting. Can you kind of dig into that a little bit? In terms of doing asynchronous, can you describe exactly what's happening there?
Okay. So we build on the technologies that we have created to manage a single node cluster, a single cluster, or how do I call it, a single location cluster. So you have a cluster of 10 nodes, let's say, tightly coupled. Each of those nodes among themselves, right, in the entire cluster, you end up having 2 copies of data. So there is some data, if there is a particular data item, we split the data items into partitions. So, the key space into partitions, which means that we have copies of partitions in the cluster on different nodes. So what happens is when you're writing into a single cluster in one location, it's tightly coupled, very close to each other, provides you sub-millisecond latency. So what I can do is I can show you the actual immediate consistency. So what happens is the write gets sent to one row, and that goes to the right place, essentially to the master, as we call it, for that partition where the key is. And then once that particular key is written to the master actually replicates to the replica of the same key. So the value is there in both places before the actual return value goes to the client, which means it's a synchronous, consistent replication strategy, okay, within the same node. Within the same cluster, sorry. Once you have that, okay, before I go further, let me point out that we don't synchronously write to disk or SSD. What we do is we signal the transaction completion to the client without waiting for the writes on SSDs to complete. But we still have written 2 copies into the cluster, and that provides us adequate durability.
Oh, I see.
Okay, so that's basically how the single cluster write works. Now, each of these cluster nodes, okay, I don't show it in this picture. If you want to do asynchronous replication, also has a separate log which it creates of the changes that are happening into this particular system. So if you go into, let's look at this particular cross data center replication architecture. Here is a customer who has a data center in Amsterdam, another one in Ohio, San Jose, and Texas, okay? So you notice there are 3 different colors of links there. So they only have 4 clusters, but they have separated it out into 3 namespaces. Now, in each of these nodes on these clusters, there is a daemon running, which is taking the log of writes in there and then shipping it to a remote cluster. And the path on which this particular shipping is happening is what is shown here. The blue one is essentially for a namespace which is shared in real time across all 4 locations between San Jose, Ohio, Amsterdam, and Texas. The green lines, the green arrows, show a ring connecting San Jose, Ohio, and Texas, and I think this customer uses it for US user data, which stays within the US in multiple locations. And then there is European user data out of Amsterdam, which they back up in Ohio. So as you see, right, you have essentially individual nodes shipping the data which is changing in one cluster to the appropriate place in the other cluster. What this means is if the master actually fails, right? If we go here, if let's say the master fails, then the replica has a copy. Not only the replica has a copy of the data for the local cluster, it also has a copy of the log with which it will use, the log which will be used to ship to the remote cluster. So it's all basically integrated into this one way of doing it.
That's great.
Okay, I have a question which is just a kind of general question. What type of companies and organizations do you think should be interested in this technology? What I'm thinking is obviously this occupies a particular position. It seems to provide an extraordinarily low latency, and I think you've kind of demonstrated architecturally at least as to why that occurs. But I'm kind of interested in what organizations would you target for using this technology? Like, what would their characteristics be?
Yeah, that's a great question. The organizations would need to actually have a lot of consumers, number one, and we've started calling this as the Internet Enterprise. So essentially, the real-time nature of the interaction between the user and the organization is extremely important here. So it could be a shopping site where somebody just shopped for something and then you want to show them a recommendation of something else they could do. And you need to do it at the time the particular shopping event is happening, or you might actually miss the boat. It is, for example, real-time advertising, as I spoke about. You need to show the right ad based on exactly what they are doing. Somebody may have just purchased a ticket for a particular trip, and then the next interaction, they're in the mood to do stuff in terms of purchasing or actual, they have a certain level of interest which is current. Then you want to actually react to it. There are things like internet gaming, where there's a lot of activity happening on games, and it's really important to be consistent. If somebody just went and bought a pony in a game, they want to make sure the pony appears with them wherever they go in the game from the next instance. You can't actually wait. And these are all things which happen at scale. It is not 1,000 users on the website. It is 1 million users on it. It is hundreds of millions in the potential pool who can come at any time. It's a sparse data lookup problem and write problem. And that's, I don't know if this gives a good overview of the kind of applications which make sense.
Well, it certainly works for me. I guess everybody that's listening in on this would actually have to come to their own conclusion. I have another question that I think is probably good for you to address. You advertise yourself as a NoSQL database, so I'm kind of interested in what is the data access language, and does that present any difficulties in using the platform?
That's another very good question, actually. Our data access languages so far has been closely linked to the programming languages that are around. So we have essentially accessors or drivers, or we call them clients, but these are basically database drivers written in C, of course. Whereas the database itself is written in C. Also Java, C#, Python, Perl, Erlang recently. We work with Scala. So you get the picture. So we basically have native APIs we have implemented in all these languages which can be used by applications. So there's a tight integration between the application and the driver, which then talks to the remote cluster. Now, in order to build a query language on top of this is not actually very hard. The hard part is, let us say, if we take the popular query language of SQL, the hard part is to actually implement all of the detailed features of SQL, which essentially make it really hard to do. So it is not so much that we are a NoSQL shop. We are basically a not only SQL kind of shop, but underneath in the database we have basically foundations like secondary indexes. We're working on transactions. We already asked it for single record transactions. We will be having multi-record transactions. We have user-defined functions. We even built for our internal use what we call an Aerospike SQL driver. So we could just write some simple SQL queries to drive it. But we are not prepared to support SQL at the application layer just yet.
Okay, I think that's good enough. I mean, so my take from that is that if you want to access in what I would think of as like fairly primitive SQL, ODBC or JDBC type commands, then you could do that. It's not you don't go to the full depth of the latest SQL standard, I think is what you're saying. Is that right?
That's exactly right.
Okay, great.
Okay, good. Well, hey, this has been very, very useful. We've been talking to Srini Srinivasan from Aerospike as part of our operational intelligence market overview, and obviously you guys have a pretty neat technology that fits nicely into some of those business cases. So thank you so much for your time, folks. We'll catch up to you next time. Take care. Bye-bye.
Thank you.